Hello, welcome back to Math 251. This is videos to accompany the lecture notes for section 15.1, which you are required to understand prior to our class on Wednesday at 5 o'clock. So we are done with derivative. We are now in a brand new chapter 15, that deal with the concept of integrations. So in Calc 1 and Calc 2, we also mentioned that in class as well, that integration is a type of fancy summations, and it can represent many different things depending on how you set it up. So let's look at the easiest examples that we have. This is probably the example that when you first encounter integrations, your teachers tells you that, well, we can use that to compute the area under this curve, right? So for example, that's one of the things that we wanted to do, but the area under the curve is difficult to find. So we opt for some sort of approximation. So the first thing you do is you look at this interval AB here. So you look at this interval AB, and then we partitioned, right? That's what partition means. You partition this interval into a smaller sub-interval, and then you construct a rectangle, right? So the notation here, this is the delta x, right? So you construct this rectangle. The reason is because the rectangle area is something that is very straightforward. If you have a point here, so let's say you have a point here, let's call it xi. So you look at the value of the function f fxi, you use it to represent the height of the function, the height of the rectangle. So you have like fxi like that, and then you have a delta x like that. So the product of these two is going to give you the area of the rectangle. So for example, this could be that area of that rectangle. And then we use that to construct a bunch of rectangle, and then we sum up the rectangle area to as approximations for the area under the curve. Obviously, if you look at this picture right here, you can see that that area is not a good approximation, but at least we get something. The thing is that we can make this approximation very precise by increasing the number of rectangle. Another way of saying that is to reduce the size of delta x, to make the rectangle skinnier and skinnier so that it can fit into that the area, the slot, right? The area under this particular curve. I'm going to give you a very quick, I mean, you've seen this before, just kind of like quickly wanted to look at this things on Mathematica here. Hopefully this can help a little bit to remind you how this is done. So I have a function y equal to x squared, very straightforward, x squared right here. I'm looking for, I want to find the area of the x squared from interval from 0 to 1, okay? So I set up my first integral, I set up my first rectangle. So this is my first rectangle. If I want to use one rectangle, I clearly partitioned, let me say that again, I partitioned my interval from 0 to 1 to 2 parts. You can see that one is from 0 to 0.5, that's one part, and then 0.5 to 1. So if I partition my interval into 2 parts, I construct a rectangle, this is what I got. Obviously not a good approximations. Now I partition my interval into 3 parts, 3 sub-interval, and then I construct a rectangle. In these situations, we do the left Riemann sum. The detail is not very important here, just wanted to show you the picture here. So I partitioned the interval into 4 parts. Now I have this 3 rectangle, and then 5 parts, partition the interval to 5 parts, and then have this 5 rectangle and so on. Obviously, the more partitions that I do, you can clearly see that the better the approximation of the area under the curve. If you use the rectangle area, all of them, sum it up, and use it as an approximation. You can see this approximation is getting better and better if you make more partitions, right? I set it up here to have eventually 40 rectangle. So if I do all the way to 40 rectangle, you can see that this turns out pretty good approximations. Let's do it a little bit more. You should be able to run pretty nicely. So this is 100 rectangle. So let me slice all the ways to 100. You can see from the visually, you can't really even tell. Like basically, this gives you the total area. So in order to get the precise answers, we define. So let me show you here. Back to this. So we define the area. Okay. So we actually define this area under the curve to be the limit of this sum when you have infinite rectangle, right? So that's the reason why we say that the integration is some type of fancy summations, and actually it's a type of limiting process. Okay, so now we are going to repeat exactly the same thing here to a function of two variable. Okay, so a quick reminder, right? By the way, that's Riemann. Quick reminder. I mean, we have seen what is what if we wanted to plot z equals to fxy. This is our x. This is our y. We know that we have a graph, right? We have a graph like that. If you wanted to plot the graph and so on. So what we wanted to do now is we wanted to say, for example, if the function is positive, right, it's above the xy plane, and I wanted to repeat the exact same idea in this kind of situations to find the volume of this object now. Okay, so previously in the Calc 1, the single integral situations, we only have an interval a to b. That's easy, right? So we partition the interval like that to set up the rectangle. So now, as you know, when you have a function fxy like this, now the domain is actually on the xy plane. So we don't have an interval anymore. Instead, we wanted to say, right, by the way, this is our y, this is our x, this is our domain. So we don't have an interval anymore. Instead, we have something that is like that as a rectangle. Let's say we have this from AB, and then this is a CD. All right, so now we wanted to find, so if you are here, let's say you are here, right? And you wanted to find the area under, the volume under this graph, okay? But on top of this rectangle. So a better picture will be a picture like this, okay? So your z equal to fxy. Obviously, if you make a rectangle right below it, and this, if you look at the region under this z above this r, right? Look at that one more time. Let me make this bigger. So you look at the regions under the z, under the fxy functions. Look at the regions under the fxy function above this rectangle r. You got a volume. Now the objective is to find this volume. I mean, I don't know how to find these volumes because z could be, fxy could be any type of functions. I do not know that, but I know how to repeat and generalize the concept that you have seen in Calc 1 and use approximations to find that volume. So again, the first idea is to partitions, right? Again, previously we have only interval a, b, so the partitions into subinterval is easier. But now you have a rectangular region like that. So we can still do partitions. We partition this whole thing now into a sub-rectangle. So the original rectangle is like that. So I break my A and B into parts, sub-interval. I break my C and D also into sub-interval. And then you look at what happens if you make this horizontal line and this vertical line. And now you can see that original rectangle is being partitioned into smaller sub-rectangle. So let's say I pick up this rectangle here, this one here, and then I pick also some points that is on this rectangle, and then now I wanted to find the area of this rectangular cube. All right, so the area of this rectangular cube, easy to do. We find, the volume of this rectangular cube. All right, I want to find the volume of this rectangular cube. So the volume is going to be this area, which we call delta A, times the height. How do we get the height? Well, we use f, okay, evaluate it at this point, right, that we call it ij, yij, put a star here, okay? So that will give us a volume. So if you construct, so the area times this gives you a volume. So if you construct all this 3D rectangular cube, right? If you construct this for every single sub-rectangle you erect, that that rectangular cube like that. So you form something that looks like this. This is for one rectangle, okay? But if you do it for every rectangle, you get this. And obviously, we can use this, okay, which is the sum of all this volume, okay? There's a double sum now because we do have the x and the y. So we have to sum up all the x, the y, with the sub indices I and j and so on. But forget about this for a moment, okay? Just look at the picture here. It should be very intuitive that the idea of looking at the volume of this individual individual rectangular cube and then sum them up, they will give you approximations of the volume of the things that we wanted to obtain. And same thing as before, this might not be a good approximation, so if we can make those rectangular cube finer and finer and finer, then we'll get a better and better approximation. The picture for this is like this, right? So these are a very crude approximation of the volume because we didn't partition our things very finely. The rectangle, we only partition it maybe like only a few. But if you partition it even more, right, you will get a better approximation in terms of the volume under the curve by summing up all those volume of the rectangular cube. So you can see, if you do it even more, you get a better and better approximations of the volume under the curve. Now, so we are going to define, okay, the volume under this curve above this rectangle, okay? So if you have, right, whatever this thing is, this is the rectangle, and you wanted to find the volume of the object, the region, the volume of the region under the curve, under the functions fxy, under the function fxy, right, under it, above r, under fxy, above r. So this region is a 3D regions, and we are going to talk about volume of that thing. The volume of that is defined as the limiting process of the rectangular cube approximations, okay? So this thing here, every single object that you see here, so this will be the height of the rectangular cube. This is the base area. So the height of the rectangular cube times the base area, so these are volume. So you sum up all those rectangular cube volume, take the limit, right? So it's a limiting process. You take the limits to indicate that now you make things finer and finer, all right? So this limits, if exists, it will give us this volume under the curve. So this is a notation for it. And not a big surprise that now you have the area component, right? This is the area component because we do have an area component here. We take the area, right, times the height to get the volume. So this is the area component. This is the height. So you can see that that height is our function here. Now this double summation will become this so-called double integral, right? So now the volume under this z equal to fxy above the rectangle r is now written like this. So that's that. Okay. Now how do we compute this? Right now we don't know. This is the only way we compute them, and this is going to be problematic because this is not something that's easy to do. Okay. So I also mentioned that before in class that even in Calc 1, when we want to find an integral, so when we find an integral, think about this, right? When you want to find this integral, x squared dx, right? You do not go through the process of, you did one time maybe, when the teachers forces you to actually use the approximation that we talk about, find the rectangle area, and then do the limiting process and so on. But if you have, let's say, other type of problems, let's say something like this and so on, you don't do that, right? You don't do this kind of stuff because it's hard to do. The sum is not easy to find, and you have to take limits. So in Calc 1, we have the fundamental theorem of calculus that says that even though this is how we define this integral, right? But when we actually do it, we have a shortcut. The shortcut is that we find something such that if you differentiate this, you get that. So this is, say, for example, something like this, right? Plus a constant. So this, you can put it in here. This is called the antiderivative. So we, instead of doing this, evaluating this using the area approximations, you actually just do this, right? So we have a way out of running this process of finding the area under the curve by looking at the area of the rectangle and so on. There's a shortcut. That shortcut is very important because otherwise we cannot do integral at all. We can do derivative, but we can't do integral because integration is so hard. So it has something to do with the area. So this concept of antiderivative, this is not very intuitive. We mentioned that in class as well. How is area problems become a derivative problem? This is not obvious. And this idea that Newton's discovery gives us a way out of computing the integral through this kind of computations. He says that it is actually the opposite of derivative, opposite of integral. Sorry, opposite of derivative, like that, right? So you just find the antiderivative and uses that. Same thing here. We are not going to compute the volume by every single times going through all these approximations. Can't do that. Okay, hard. It's very difficult. So we have a way out. The way out is called iterative integral. This is funny that everybody knows about Newton's, but this is also very important. This idea is it's come from, we call it the Fubini method. Actually, Cauchy knows that from before, some historical perspective. We are going to talk about how to actually do that, okay? How to actually use this kind of iterative integral, a shortcut, a way out of this madness of using rectangular cube to find the volume. So that will be the things we're going to talk about next. So I'm going to do it in the next video, and I will see you there. Thanks.